Hi, my name is Melissa Micah. I'm with the Hydrologic Engineering Center. Welcome to Regional Precipitation Frequency Analysis, Part 3, Methods of Regionalization. In this video, we're going to talk about different regionalization methods. This table is taken from Hosking and Wallace 1997, which we'll talk more about in Part 4. This table summarizes the different regionalization methods that are commonly used. The first one to look at is at site. This is probably something you've done before, where you take a single gauge, estimate the mean, dispersion, and shape just from the data at that single site. The next method to look at is called index flood. This method uses the at-site mean, but it estimates the dispersion and the shape parameters using a regional average. The next is fractional membership, which uses an at-site mean, and instead of just using a regional average for dispersion and shape, it uses a weighted average of regional estimates, which we'll talk a little more about how that's done. Next is region of influence. This also uses the at-site mean, and it estimates a weighted average of at-site estimates for sites that are located within that site's region of influence. And lastly, we'll talk about mapping, which is a way to estimate dispersion and shape using an estimated function of site characteristics rather than just the regional average. I also want to point out Bulletin 17. You're probably familiar with these methods by now. We've talked about it in some other lectures in this class. Bulletin 17 uses at-site mean and dispersion, but it uses a weighted average shape parameter. You might recognize this from SSP when we perform Bulletin 17C analyses. There is an option to use a weighted average of the at-site and the regional skew. So the first method we're going to talk about is the index flood. This is a very common method of regionalization. The idea behind index flood is that sites in a homogeneous region have the same distribution, except for a site-specific scaling factor, which we call the index flood. For hydrologic parameters such as precipitation or stream flow, we usually use the mean annual maximum value, or L1 or L mean, as our index flood value. Predictions for a site using the index flood method start by using the site index flood, which is typically just the mean, and multiplying it by a regional growth curve. So for example, how that might be calculated, if you have a regional growth curve, the mean is always equal to 1. You multiply that by the site index flood, which is typically the mean of the site. In this example, it's 2.5. That gives you the predicted site frequency curve, which will also have a mean equal to the index flood. And let's show an example of what that might look like. Let's say here we have a regional growth curve that has a mean equal to 1. We multiply that by our site index flood, which scales up the curve to yield our predicted site frequency curve. So as we saw in the table on the previous slide, index flood uses the at-site mean and the regional average, dispersion, and skew, which is how we develop the regional growth curve. This is helpful because it gives us more robust estimates of the dispersion and the skew as opposed to using just an at-site value for all parameters. The limitation is that everywhere where you want to apply index flood, the site has to be located in a distinct region. This can also cause issues with sharp boundaries where two adjacent regions meet. Next, we'll talk about fractional membership. Fractional membership is very similar to index flood, but instead of establishing very strict definitions of regions, the assignment of sites to regions is a little bit more fluid. The process starts similarly to an index flood analysis, where you estimate regional averages of the dispersion and the skew. But instead of applying a single regional growth curve for each region, you use a weighted average of all regional growth curves from all regions and weight them according to their similarity. So if we break down this equation a little further, we can predict the site frequency curve by multiplying the site index flood, just like the index flood method, by the regional growth curve for a specified region and weighting it by its similarity to site I. In this way, we incorporate the regional growth curve from many regions rather than just a single region. This helps us fill in the gaps between sites a little bit better and also produces a more continuous map that doesn't have distinct boundaries, like the index flood method did. Next, we'll talk about the region of influence method. This starts differently than the index flood and fractional membership methods. The idea behind region of influence is that each site is considered its own region. For each site, select K similar other sites from the surrounding area and combine those to compute a regional average L moment ratio. In that way, each of these is considered its own region, computes regional L moment ratios, and estimates the regional probability distribution directly, and this happens for every single site. The number of sites used in each region can vary from site to site. The last method we're going to talk about in this video is called mapping. The goal of mapping is to explain how L moment ratios vary in space. Mapping allows you to provide estimates anywhere that you can reliably predict, even if you don't have any measurements at that location. And it helps avoid assigning particular locations to a single region. This is helpful if you have regions that are overlapping or non-continuous. With spatial mapping, there are two general approaches that you can follow. The first is interpolation, and the second is spatial regression. Interpolation is where you have no physical explanation for the variation, and the results are dominated by the nearest observation. This should be a familiar concept to you, where you have individual points, and you interpolate the spaces in between based on the closest values. With spatial regression, you build a regression model that explains why there is spatial variation. Usually you use spatially based predictors in the model, like mean annual precipitation, temperature, elevation, distance to coast, location, etc. Spatial regression is the method that's used most frequently in regional frequency analyses because it typically provides a more informed estimate. In a practical sense, mapping is where you produce a spatial map of the L moment ratios, like LCV and L skew, and from these maps you can interpolate virtually any location, even if there's no observations. And from these maps, you can estimate the parameters of the frequency distribution from virtually any location within your study area. Here's one example of using interpolation versus spatial regression. In both of these, mapping was performed for the second L moment ratio, LCV. In the left, an IDW interpolation was performed, and in the right, there was a region-level spatial regression. As you can see in the interpolation on the left, the estimates in between sites are entirely based on the value of that location. So this location here, where there's kind of a bullseye, could mean that the LCV of this site is an outlier and is heavily weighting the areas around it. The interpolation may not be capturing the physical behaviors going on in this region, which is located in the Pacific Northwest. In contrast, the spatial regression assumes that the L moment ratios and the characteristics are related because these are a homogeneous region. Elevation and annual precipitation were used to develop this spatial regression, and you can see that the model captures greater spatial variability than the interpolation model. Lastly, we'll talk a little bit more about spatial regression, and specifically which parameters to regress. For L1, which is the mean, those are typically predicted at the site level, so we're not using any regional estimates, and it's typically using a precipitation predictor for precipitation frequency analyses. This tends to be a very strong predictor for the mean, such as mean annual precipitation. For T, which is the L moment ratio LCV, there's substantially more error in the estimators, and so you might decide to predict this at the site level, at the subregion level, which is a collection of sites, or at the region level. For T3, which is L skew, and T4, which is L kurtosis, these are typically estimated at the region level or even larger because the sample error is substantial. And so as we mentioned, the higher levels of L moment ratios have increasing sample error. And so we tend to estimate those at a more region level than a site level. In summary, there are many different regionalization methods, starting with at-site estimation, and we talked about index flood method, fractional membership, region of influence, and mapping. These all provide different options for estimating the dispersion and skew using regional averages or some other method rather than just relying on the at-site estimates. More sophisticated regionalization techniques can help produce spatially coherent frequency maps. Rigid regions, such as found in index flood method, can create mapping artifacts that require smoothing. That is, we might have distinct boundaries between two adjacent regions. That concludes the video for part 3. Please continue on to part 4 of regional precipitation frequency analysis.